Many people have suffered from severe burns, and oftentimes the treatments are wound dressings or sutures. These types of treatment can oftentimes prolong patient pain and trauma and also increase exposure of the wound to bacteria. Therefore, a promising new treatment is a hydrogel. A hydrogel is a three-dimensional network that is formed between two molecules with with many properties that are cross-linked together. The hydrogels that I worked with consist of a cross-linker, either NHS or maleimide, and a dendrimer, either NH2 and thiol. These cross-linkers and dendrimers are dissolved in a phosphate and borate buffer, and then these two solutions are then combined together. Because hydrogels have a future application on humans, we wanted to find two buffers that, when combined, would create a pH of 7.5, which is similar to the pH of human blood. Therefore, we found, after many experiments, that a 0.3 molar phosphate buffer solution at a pH of 6.5 and a 0.1 molar borate buffer solution at a pH of 8.6 would combine together to result in a pH of 7.5. Therefore, as I have prepared here, I have a cross-linker dissolved in the 0.3 molar phosphate buffer solution and a dendrimer dissolved in the 0.1 molar borate buffer solution. So in order to create a hydrogel, essentially, all you do is you pipette equal amounts of each solution into a little cap, like this one. And usually this is done in ice conditions, so the cap is usually put in ice, and also these are kept in ice to keep them cold. And so the dendrimer is always pipetted into the cap first, followed by the cross-linker. And then you kind of pipette up and down a couple times to mix them thoroughly. And that's really all that it is. Afterwards, the cap is put into the fridge to where it's kept until the gel fully forms. Usually the gel forms between 3 to 10 minutes. And so with the two hydrogels that I worked with, the first one, the NHS and the NH2, formed very nicely in ice, and that was very successful. However, the second hydrogel that I worked with, consisting of maleimide and thiol, did not form very well and was unable to maintain a nice shape. The reason for this is because when the thiol was dissolved in the borate buffer, deprotonation occurred, and the thiol began forming disulfide bonds with itself. So therefore, once the thiol and borate buffer solution was combined with the maleimide and phosphate solution, the network wasn't the same, and it was weaker, because rather than only bonding to the maleimide, the thiol was also bonding to itself. Therefore, when the thiol was dissolved in the borate solution, it was turning kind of a light pink color. So to deal with this problem, we found that by adding a reducing agent such as TCEP to the borate buffer, that would remove some of the disulfide bonds between the thiol molecules. However, we did not know how much TCEP to add. Therefore, we experimented with the control group, and the control group that consisted of only borate buffer and thiol, and then we also had experimental groups with different amounts of TCEP with the borate buffer. We tested the absorption spectroscopy and found that after 2 to 5 days, the control group and the experimental groups actually yielded very similar results, which means that in our experiments we did not add enough TCEP to remove the disulfide bonds. In the future, we're going to continue to work to determine how much TCEP to add, and also with both types of hydrogels, we're going to put them through rheology testing to determine their viscoelastic properties and their mechanical strength, and we're also going to do swelling studies to determine how much water they can take in. Both of these results will help us determine what type of hydrogel will be the most effective at treating human burn wounds.